The next talk of the day is Fourier Principal Component Analysis, PCA, Ying, Xiao.
Thanks, Prasad, for the invitation and the introduction. So this is joint talk with Naveen Goyal and Santosh Vampala. Okay. So I guess before I start, there should be a disclaimer that these Fourier transforms are actually taken over Rn. So if anyone wants to... So what I'm going to do is I'm going to describe a machine learning problem for you. And then, relatedly, I'm going to develop an efficient tensor decomposition, which will solve this problem. And in between, there's going to be a little bit of Fourier analysis, some derivatives. Be a good time for the next 45 minutes. Okay, so let's start with the learning problem. So the learning problem is called independent component analysis, and this is kind of a big deal in machine learning and statistics. I'll give a little more background in a little bit, but the problem goes as follows. So you start with a random vector S. It's fully independent, so it's a product distribution. And just as a caveat, none of the SI components are Gaussian. And so what you see are not the S's, but you see some fixed linear combinations of the S's. So you see AS. A is a fixed matrix. Just to normalize it, we'll say that it's a full row rank and all the columns. AI have unit norm. And so what happens is that you see independent samples of this form, and your goal is to compute A. So here's a picture that should describe the situation more clearly. You start off with some type of product distribution for S. This is your random vector. So you can think of, for example, a uniform distribution over a hypercube. Get independent samples from this distribution. It's the green points there. But unfortunately, those are not the points that you see. Rather, you see a product AS. So the uniform over a hypercube becomes some type of parallelepiped. And your goal is to recover that parallelepiped, that map A, only from samples. So all you see are the... No, you only know that the S's are independent and not Gaussian. So yeah, no distributional assumptions at all otherwise. So the way to think about this is that you have m random variables and you're taking linear measurements of them. And you want to recover A, the measurement system. So the way this problem crops up is that it's kind of used as a general dimensionality reduction tool. So when you have some data, you run PCA, that doesn't work out so well, you go to ICA and random projections. It's standard enough that it's in this I guess this Bible, the elements of statistical learning, and that's what that citation there is. Recently, it's gained traction in these deep belief networks. So if you've been following the New York Times, Google has been building these really big neural nets, and this is used to sparsify the layers. Actually, though, the problem has been around for a long time in signal processing. It's called blind source separation, deconvolution, or cocktail party problem. We're trying to resolve individual sources from linear combination. There's a ton of literature on it, and so the standard reference is Hyvarinen et al. And even more practically, and this is actually going quite a ways from theory, it's used in finance, biology, and apparently when you get an MRI taken, they try to deconvolve ICA actually. Okay. And just a little bit more background on the problem. So the problem's been around since the late 80s. The first people to really formalize it and pin down the problem were Newton and Hérault. And it really came into theoretical computer science through this paper of Fries, Jerem, and Kanan in '96. Recently, as of, I guess, last year, there have been some provably good algorithms for it in important cases, but not in full generality. And of course, there are tons of heuristics, tons of things that people do in practice in signals processing, which don't have any provable guarantees. Okay, so let's talk a bit about the standard approach to these independent components problems. Standard approach, one thing you could do is to just try straight PCA. So you take your data X, you form the covariance matrix, XX transpose, and then you just look at the eigenvectors. And the hope is that the eigenvectors will give you the column. That's one formulation. Another formulation is to consider the second moments. This is essentially the same thing. And this is just the usual principal component analysis. Now, the problem with this is that it works. It works okay. When all your eigenvalues of your covariance matrix are degenerate, so if you have a degenerate subspace with the same eigenvalue, then you end up with mixing in the eigenvectors, right? And this essentially prevents you from recovering the columns of A. This is more of a problem when you consider the fact that one of the usual things you do when you see data is that you put an isotropic position. So you make all the eigenvalues 1. It's a standard normalization, and it pretty much breaks your ability to use PCA. Okay, so PCA is defining a contrast function using the second moments. A very natural thing to do is to just try higher moments. Fourth moments are particularly nice. And what happens if you massage the fourth moment a little bit is that you end up with some type of tensor decomposition that you're trying to compare. So the fourth moment is best represented as a tensor. So an array in n by n by n by n dimensions. And in the independent components case, you end up the fourth moment tensor ends up being just a sum of outer products of rank 1s. And if you could recover the rank 1s, you would be done. Now, this is tensor decomposition is a pretty hard problem in general. But in the particular case, when all the AJs are linearly independent, you can in fact assume that they're orthonormal. Then the local optima of this tensor suffice. So you have a tensor, you view it as a four linear form, you find the local optima of this thing on the sphere, just like you do for eigenvalues, cover the AJs this way. So this is really standard and has been around since the 80s as well. But essentially what happens with all these algorithms is that, as I mentioned on the previous slide, you require the columns of A to be linearly independent, which pretty much means that A has to be full rank, n by n, which means that you can only deal with the problem when you have as many measurements as underlying variables. And what I mean by that is that the dimension of x here lives in Rn has to be the same as the dimension of S, the fully determined case. A second standard assumption that people make when they analyze these algorithms is that each component of the vector S differs from a Gaussian in the fourth moment. So a Gaussian's fourth moment is 3, so your fourth moment is bounded away from 3 by this quantity delta. So yes, I guess the key point is that this precludes the underdetermined case. When A is a fat matrix, you're taking relatively few measurements, so X is a smallish vector, and S is lives in a really big. Okay, so what we do in our paper is we make a good amount of progress on the underdetermined case, so where A is fat, and we also are able to relax the assumption that you're bounded away from a Gaussian moment in the fourth moment. And informally, our main result is as follows, that if you have an underdetermined model, then in time, which is polynomial, and by polynomial I mean depends on several parameters here, you can compute columns of A. You can recover A. The key parameter is this thing here. Where is that pointing? This thing here. And what this is as follows. So you look at each column of your matrix A, and you tensor it up with itself some number of times. And you want these things to be linearly independent. And the intuition for that I'll explain in a little bit, but this is sufficient for what we want to do, and we believe it's necessary but we can't prove it just yet. Okay, so that's our major result. Yes? Okay, so for some. But I mean, your complexity also depends on which moment it is, right? Because it's harder to sample for higher moments. Oh, why are you saying? Oh, sorry. The reason is if I have, let's say, S1 and S2 is Gaussian, and I take a linear combination, then it's still going to be Gaussian in any two directions I pick, right? So it's not identifiable. You can't uniquely recover it. It's okay if you just care about the subspace of Gaussians, that's fine, but you can't do anything uniquely. Any other questions? Okay, so I keep talking about this underdetermined thing. Let me explain it a little bit more. So once again, S lives in in Rm, where M is relatively large. So we have our uniform distribution over cube. It's a product again. You have independent samples there. The matrix A does two things. First thing it does is that it turns, for example, this uniform distribution into a parallelepiped. But what happens afterwards is that you have a projection. And so you lose tons of information. So I guess it's a little bit surprising that you can solve the underdetermined case at all. Okay. What am I doing? Okay, so, it's kind of a lot of math on this slide. It's not as nice as I thought. So our basic algorithm is actually relatively easy. So what you do first is that you pick a random vector u. And this is going to be a random Fourier coefficient of the overall distribution that you're interested in. And for each point in your sample x, say, you just compute the Fourier weight, so exponential of IU transpose x. So yeah, I guess my Fourier transforms are going to be over Rn and not over the Boolean hypercube, say. What you do next is that this gives you the weights, Wx, and we just normalize it. With this denominator here, it's not a big deal. And then what you do is that you just form the covariance matrix and you stick these weights in the obvious way. So that's what this is. You have your normal covariance matrix terms here, XX transpose, subtracting off the mean, and then you just stick in the weights. So this is essentially just a reweighted covariance matrix. And what you do then is that you just compute the eigenvectors of this reweighted covariance matrix. And basically, magically, the eigenvectors end up being precisely the columns of A. So this is like the basic scheme. This only works for the fully determined case. You have to do something quite a bit more complicated for the undetermined case. So this algorithm is actually based on an idea by Yeridor from like the early 90s. But giving an analysis of this is actually a little bit non-trivial. So the question is, why does this possibly work? Why does just throwing in Fourier weights into your covariance matrix help you at all? And basically, it's this Fourier differentiation multiplication relationship. So if you want the Fourier transform of a derivative of a function, then in the Fourier space, it's just the same thing as multiply by your Fourier variable. So that's actually the underlying thing that's going on here. What we actually end up doing is that we end up considering the log of the Fourier transform of the distribution. So in which case, if you take a few derivatives, that's what this d squared is, you end up with a Hessian matrix. And that's actually exactly the Hessian matrix on the previous slide. And this Hessian matrix has this following form. On each side, you end up with an A and an A transpose. So this is looking good, right? This looks like a usual diagonalization. And then the diagonals are these functions g. And what these g's are, they're the univariate derivatives of the log of the Fourier transform of each individual Sj, sorry. So if everything were real here, you would just have A, diagonal, lambda I, A transpose, you diagonalize, you go home, you're done. Everything works great. So I guess the sticky point for this is that this is actually a complex quantity. So this is not a normal matrix, it's not Hermitian. So you have to work a little bit harder. Yes, that's actually critical. You have to anti-concentrate the eigenvalue so that you have spacings.
So is that the reason why Fourier?
Yeah, that's essentially the reason why it works. It's a little bit tricky because in the undetermined case, the A here, there are dependencies now, but I'll go into that in a little bit. Okay, so that was sort of the quick and easy version for the fully determined case. For the underdetermined case, you have to do quite a bit more work. And so these are the little hammers that we're going to hit our problem with. So once again, we're going to look at the log of the Fourier transform of the distribution over X. And what we're going to do is that we're going to compute the derivative tensor of the log of the Fourier transform. And so when you have a function that's multivariate and you differentiate it once, you end up with a gradient vector. You differentiate it twice, you end up with a Hessian matrix. Differentiate it 3 times, you end up with a tensor. So this is where the tensor decomposition will come in. And actually, because it's a derivative function, right? So you have a derivative tensor at each point of space. So it's actually a tensor field. And so what we're going to do is we're going to evaluate the derivative at 2 randomly chosen points, u and v now. So not, in the fully determined case, we only needed 1 point u. And then this will give us 2 derivative tensors tu and tv. And then we just perform a tensor decomposition on tu and tv to obtain the matrix A. So that's kind of the scheme. It's
T is a function of R.
t, this thing? No, this is a derivative operator. How many times you have to take the derivative? This depends. This depends on how underdetermined you are, right? Essentially, you have to take enough derivatives so you have enough degrees of freedom to deal with the fact that you have m random variables. Okay, so I keep talking about these derivatives, and I guess we can actually compute them out explicitly. It's not so painful. So let's start with a really, really easy case when your matrix A is just an identity matrix. So someone's literally giving you S. So we have our log of our Fourier transform, and let's differentiate it. So there's kind of a lot of math on this slide too, but the idea is really easy actually. So when you have a Fourier transform and these S's are fully independent, I can separate the Fourier transform into the product, right? The product of each individual guy here, like this. And now when I take the log, this product becomes a sum. So this log of the Fourier transform just becomes the sum of the log of the Fourier transform of each particular SI. Now when I differentiate with respect to the variable ui here, ui only appears in one Fourier transform, that of SI. And that means that I will end up with a term that depends only on ui when I differentiate with respect to. So there are no u2s, u3s, etc. here. So the point is that when I differentiate once, my derivative depends only on the variable I differentiated with respect to. So basically, I guess product distributions play very well with the Fourier transform. This is like the same idea when you try to prove a Chernoff bound, right? Where, sorry?
Should be IS.
Oh, yeah, sorry, I dropped off. Yeah, suddenly. My bad. Yeah, it doesn't make any difference just because they all pop out. Sorry. Okay, so each component of my first derivative depends only on the variable I differentiated with respect to. So if I differentiate twice now, and I look at the Hessian matrix, all my off-diagonal terms are 0. Okay? And all my diagonal terms end up being some nasty expression I'm not really that interested in. I'll talk a little bit about that later. And if I keep going with general derivatives, what happens is that because my second derivative is already diagonal, my general derivatives will also be diagonal. And so, and by diagonal I mean in the strongest sense for tensors, so that only the I coordinate is non-zero, and everything else is 0. And so let me just reiterate this one key point, that the higher derivatives are represented by tensors, but I get to have one tensor per u I evaluate at. So there's an infinite number of these things to work with, if I so choose. Okay, now that was the really easy case when A was the identity matrix. What happens when you use A, which is not an identity matrix? And this is more general than just the basis change. This is actually any matrix. We have to work much harder, basically. But if you do it for the second one, you end up with the A's popping out on either side. And notice that the argument is basically column J of A in a product with U. And so that's the second derivative. If you go for the general derivatives now with the matrix A, then you have to work still harder. But what you end up with is an outer product decomposition, where the dth derivative is the sum over outer products, d outer products of the columns of A, and then some coefficient, which I'm going to call g again. Yes, g sub j, sorry. And these coefficients are dependent only on this A transpose U of j. So what I mean to say is that all your derivative tensors, independent of where you choose to evaluate them, have the same outer product here. And what you want to do in principle is compute what the outer product decomposition is. But we have an infinite number of tensors to work with. It turns out we need only 2. But let's take a look at what happens if you only look at one of them. So if you look at only one derivative tensor, well, actually you can forget about derivatives. You can just consider a tensor of this form. If someone gives you a tensor of this form and asks you to recover the AJs, when is this possible and when is it computationally efficient? And basically the answer is never. It's NP hard, and I only know of one class of tensors where this is actually possible. Okay, and by one class of tensors I mean when your tensor is of order greater than 3. When the order of your tensor is 2, it's just the usual eigenvalue decomposition here. So this is reasonable to do. When the order of your tensor is greater or equal to 3, so it's an n by n tensor or larger, and when your AJs are linearly independent, then you can do this tensor power iteration, which is basically just the analog of the matrix power iteration for computing. However, because of this condition, because the AJs have to be linearly independent, it implies that you can't consider too many AJs. If your tensor decomposition here has too many things, you can't find them. And just as an aside, and this will be important later, this is related to Prasad's earlier question, your lambda j's had better be different here, or else you're never going to recover the AJs uniquely. It just forms a So trying to decompose the tensor when you only have one tensor is going to be really hard, but we have an infinite number of these tensors, and actually we can just use 2. So let's pick some mu's, some lambdas, and let's say we have 2 tensors with the same vectors in their outer products. Then what we're going to do is that we're actually going to recover the AJs from this pair here. And the actual algorithmic technique is that we're actually going to take these tensors and we're going to flatten them down to a matrix. So you define some map between, say, a 4th order tensor, an m by n by n by n tensor, and you just turn into an n squared by n squared matrix. So you'll end up with something like this. You'll have the diagonal of the coefficients, and then On each side, you'll be conjugated by the vector of the tensor powers, the d over 2 powers, of the columns of A. So basically what happens is that you split half of these factors, and they go to the left, and half of these factors, and they go to the right here. So if you're given these two tensors and you want to decompose it, the algorithm is relatively simple. So, okay, I'll just explain this as follows. You flatten the tensors down to m mu and m lambda first. And step one, just make sure that m mu and m lambda are full rank. So we can start taking inverses. And then what you do is you take m mu and m lambda, which are now full rank because of the w's, and you just multiply m mu with m lambda inverse. And this gives you another matrix M. And then all you have to do is you take M and you compute the eigenvector decomposition of it. And once again, M is not normal. It's not Hermitian or unitary or anything nice. So it has to be a general eigenvector decomposition with an inverse. And then you take these eigenvectors, say each column of P is called Pi, and you basically stick it back into a tensor, and you extract the best rank 1 component there. And for this, you can use the tensor power iteration, because it's just 1. It just has 1 component in the rank 1 in the rank 1 sum. And then once you do that, you have to clean up. You have to make all the extracted vectors real again. That's not really that interesting. So, yeah, I guess the takeaway from this slide and for most of this talk is that you have two tensors with the same vectors in their outer product decomposition. You take one, you squish into a matrix. You take the other, you squish into a matrix, take its inverse, and then you diagonalize. That's the major idea. And so, if you look at the actual theorem that you can prove about these things, as Prasad said, you need the coefficients to be different from each other. But once they're different from each other, and once your AJs are not in the tensor space are not linearly dependent, then you can go ahead and recover the AJs up to whatever accuracy you want in polynomial time. So yeah, the point here is that decomposition of one tensor is too hard. Decomposition of pairs of tensors is relatively easy if you're careful about it. Okay, so this might be a little bit surprising, but the basic idea is pretty easy. So we started with tensors t mu and t lambda, and we squished them down into matrices m mu and m lambda. And let's pretend m mu and m lambda are full rank. If I do so, then, and I multiply m mu by the inverse of m lambda, so then you get basically 6 terms. The first 3 correspond to m mu, the last 3 correspond to m lambda inverse, and because they share the same outer product decomposition, I basically have 2 cancelling terms here. And in that case, I end up with my vector of tensor powers of A, a diagonal matrix which corresponds to mu j divided by lambda j, and then an inverse here of the tensor powers of A. So if you look at it, this is P, D, P inverse, and so these are the eigenvectors. So this is really easy if you're interested in the exact case. In the robust case where there are perturbations, so where you have m mu plus some error and then m lambda plus some error, diagonalisability becomes a bit of an issue. And by which I mean the following. If I have a matrix A, and I can write it as P D P inverse, what happens when I look at A plus perturbation? Can I still write the same thing? And in particular, what do I actually need for diagonalisability? So one thing I need is I clearly need my eigenvector matrices to be invertible. Otherwise, I shouldn't be writing P inverse anyway. But a characterization of diagonalisability is when your minimal polynomial has non-degenerate roots. Now, the minimal polynomial is not something I'm very good at working with, but a sufficient condition for diagonalisability is that all your roots, by which I mean all your eigenvalues, are non-degenerate. So once again, this comes back to Prasad's question. My eigenvalues have to be well spaced. I want to be robust about this. So when I take my matrix M and there's some perturbation, when are the roots well spaced? If the eigenvalues of M are well spaced. And in the normal case, you just apply this Weyl inequality. No eigenvalue moves too much. Because my eigenvalues are real, they're well ordered as well. And my eigenvalues move at most by the spectral norm of my perturbation. So in the case when your matrix is not normal, not Hermitian, there are kind of a couple of things that you can try to do. One is the Bauer-Feich theorem. And what this says is that every eigenvalue of your perturbed matrix is close to some eigenvalue of your original matrix. Now the problem with this is that all my eigenvalues of my perturbed matrix could in principle be close to a single, like lambda 1 of my original matrix. So this prevents you from getting any decent type of spacing result. The other thing there are some other results, but they essentially assume that your perturbed matrix, A plus E, is already diagonalizable, which is just exactly what we're trying to prove. So that's not helpful at all. So one of the things we have to do is that we have to prove sort of a generalized Weyl inequality. So when you have a diagonalizable matrix and its eigenvalues are well spaced and then you perturb it, then you can come up with a mapping between the eigenvalues now, which is bijective here, and where the bijection doesn't change your eigenvalues much. So the proof of this is via a homotopy argument. If you know the Gershgorin theorem, there are certain strong variants of that. And you have to use something like that. Okay, so in terms of the analysis of the tensor decomposition in the robust setting, you apply this inequality. Then you have to apply some eigenvector perturbation bounds. Once again, because we're not normal, we can't use Davis-Kahan, the sine theta theorem. We have to use more general things. We use a result of Ibsen and Eisenstadt. This means that your eigenvectors are now close to the vector of the tensored up AJs. You apply tensor power iteration. That step is robust 2. And then, so that's the tensor decomposition that we developed for this. Now, the question is, how do you use it to solve the underdetermined case? And it's actually really easy. So just as a quick reminder, underdetermined, x equals AS. A is a fat matrix, so you're taking fewer measurements than there are underlying random variables. So you pick two random vectors, u and v. You form these derivative tensors, tu and tv, and then you just run the tensor decomposition on it. So that's our algorithm. Okay, so one thing I should mention before we go over any further is how do you actually estimate these derivatives? And because of this Fourier differentiation multiplication relationship, what you can do is you can just sit out there, grind out the derivatives using the quotient rule. It's a little bit unpleasant. So if I just look at the fourth derivative tensor, this is just one term of it. There are products of all these exponentials, all these polynomials. So actually there are something like 17 more terms of this form. So it's really not very pleasant. But the salient point is that if you consider the number of derivatives you're taking to be a constant, then you basically have d to the d. Each one is really easy to estimate empirically because as long as your moments are bounded, these things are bounded. So it's not a big deal, it's just kind of gross. Okay, so then in the underdetermined ICA setting, we end up with a similar theorem to what you saw for tensor decomposition. That you have dependencies on how linearly independent the tensor powers of your columns of A are, and you have a dependency on how much your moments differ from a Gaussian. And so I write CUM there for cumulant, and this is basically just it's a polynomial of the moments. It's not substantially different. Okay, so I have a little bit of time left, so I can talk about how you actually prove this. So Yeah, it's the overall scheme should be relatively clear from what I said earlier. So if you take a derivative tensor at u, you end up with something of this form. The diagonals are going to be the dth derivatives of the log of the Fourier transform of each variable. And so now we just have to show, by applying our previous tensor decomposition theorem, that the quotients now are well spaced between when you take a u and a v. So if you want to show your quotients are well spaced, this is where the math actually comes in. Okay, so what you do is that you take the dth derivative, these diagonal terms, and you Taylor series expand it. And what you do is you truncate the Taylor series at where you know the moment difference is. This is only for sake of analysis. You don't actually have to know this while running the algorithm. And so you have a remainder term here from the Taylor series, but you know the remainder term is bounded, and in fact small, basically because you know of the existence of one more moment. And then so the scheme is this is a finite degree polynomial. We're going to anti-concentrate that using a polynomial anti-concentration inequality, and then we're just going to bound the tail error and make it small relative to the anti-concentration. So the tail error first, like I said, is just a dth derivative of a log of the Fourier transform. For the Fourier transform, I know that the dth derivative is less than the dth moment. Sorry, that's meant to be a d there, not a k. So what you do is you apply the quotient rule, you count the number of terms you have. It's not too big, it's like d to the d, and you just have a moment bound. So the tail error is really easy. The polynomial anti-concentration in the finite polynomial part, you need something which, I mean, it's essentially a univariate polynomial anti-concentration inequality. So I guess the usual way of getting these is through this Carberry-Wright result, right? The problem with that is we only know something about one coefficient, so that's why I'm talking about monic polynomials here, the highest order coefficient. And in fact, the other coefficients could be bounded. You could have really big gaps from Gaussians at some other step. So, and then you have to integrate this LP norm of the polynomial over your measure. It's a little bit tricky. But you can do a similar thing using much easier techniques. And there's the proof, but the picture is much easier. Okay, so let's say that I have a degree d polynomial. Then for any band around around 1, for example, and I can only cross that band d times. This is basically because you need a sign change in your polynomial to cross back into the band. Each band is of not too high width because I know the polynomial has to change at least a certain amount in any interval, and this is I guess lower bounded by the Chebyshev polynomials. And then I just basically take the product. I have this many bands, they're this wide, and the Gaussian measure is at most 1 over sigma square root 2 pi, right? So that's where the polynomial anti-concentration bound. So, okay, so once again, we're not actually anti-concentrating a particular g. We actually have to deal with these relatively unpleasant quotients. You basically truncate, play some probability tricks. It's not terribly interesting. But once again, your spacings surprisingly end up depending on the on how linearly independent your tensor power is. And so you prove that any two anti-concentrate, then you just union bound basically. Okay, so that pretty much concludes the technical part. So now you have anti-concentrated diagonals. You just run the tensor decomposition. You're done. Because we're using the Fourier transform over Rn, you can actually do some additional nice things. One thing you can do is, let's say that you have a Gaussian noise here, an eta, of any Gaussian which is independent of S. then you can actually remove it. And basically the way this works is that this eta is invariant under taking Fourier transforms because it's Gaussian. Another thing that you can do is that you can prove, you can give a result for a Gaussian mixture model. So the way the Gaussian mixture model works is that there are k Gaussians. Someone's picked ahead of time, and when you see a sample, you first pick a Gaussian with weight wi, and then you pick a point from that particular Gaussian. And so the goal is to recover the parameters of the Gaussians. And so we can do this for when your number of Gaussians is at most your dimensionality. So I guess this is another proof of the result by Xiao and Cacard, except I guess we can deal with Gaussian noise too. Yes? Sorry, spherical Gaussians only at this point. So that's actually like the major open problem here. Can you do anything for non-spherical Gaussians, right? You probably have to do something like the underdetermined tensor type techniques because there are just too many parameters that you're trying to learn that you're not going to get from just a matrix, right? Right, sure. As far as open problems goes, there are some generalizations of this independent components model called independent subspaces, where your random variables S are split into subspaces which are independent, but within the particular subspace, it can have very complicated dependencies. And this is really the thing that people use in these deep. So it would be nice to be able to prove something there. A more vague hand-wavy question is, what is the relationship between our method and kernel PCA? It looks a lot like it, but it's not quite the same thing because when you do kernel PCA, you end up with a... So I think it looks similar, but I'm not sure what the connection is there. And of course, the Gaussian mixtures. Okay, and I think that's it.
Why did you need to take the complex characteristic function and the real characteristic function? Is there a particular point?
Oh yeah. If I take the real characteristic function, I better hope that all my all moments exist, right? If I'm just taking exponential of u transpose x, right? If x has infinite moments, then life is going to get complicated, right?
And why is that not an issue with the complex characteristic?
Oh, because that only becomes a phase factor at that point, right? If u transpose x gets really, really big, I'm just going around on the unit circle in the complex plane, right? It's like the Fourier transform always exists, but like the Laplace transform doesn't, right? Yeah, that's the other thing. All the previous ones, well, I guess. Okay, yeah, we can deal with heavy tail distributions is why you take the complex.
Manifest